coming. This is our very special event related to the focused product release of Gaia. As all the releases, this takes a lot of people and a lot of effort to prepare. We have an honor to be part of the FPR thanks to Nami Mowlavi, but he basically based his work on the team from Geneva and basically all people that are involved in SIL7 and the BCG. I'm replacing today Laurent here, who should be here and speaking, but he was caught by some vicious virus. And our first speaker is Holl, specialist of classification, many other things. He's going to introduce Gaia. Then we go to Nami Mowlavi, who's going to talk about long-term variables in FPR. Thank you and welcome.
Oh, hello everyone. So I'm talking today on behalf of Deepak and SIL7, and also on behalf of Laurent, who unfortunately cannot be here due to sickness. What I will be talking about shortly is just to give you a sense of why Gaia is an ESA cornerstone mission and why it's so important. So Gaia makes observations of a lot of stars. It doesn't mean thousands, but it actually means billions and billions. And this goes down to magnitude of 20, magnitude, extremely faint. And Gaia basically does it in a systematic way of all sky and multi-epoch. So we'll see what that means exactly. So it does a all sky survey. So what does it measure? It measures several things, and this is quite specific for this mission. It does, first of all, astrometry. Now, astrometry is not what a lot of missions or observatories do. But astrometry literally means the measures of stars, their motions, and it measures the positions of stars, it measures the motion of the star and the parallax, which is related to how far objects are away. And it does it so precise that it needs a dedicated design of a satellite. But on top of that, it also measures things like brightness and color, which are the typical things most surveys observe. And then on top of that, it also measures radial velocities for about 100 million stars, which is also quite unique to have combined with all these other measurements together. And this for a price of less than 25 cents. So it's a very cheap machine. So where is Gaia? Gaia is actually located not in an orbit around the Earth, but in an orbit with the Earth at the Lagrange point 2. So Lagrange point 2, as probably most of you know, is moving along with the Earth-Moon system around the Sun, same angular velocity, so it stays basically fixed in the sky from our position, seen from the Earth. And it has basically an almost unobstructed view of the whole sky. So we can do an all-sky survey to observe. This is also where Webb is located, for example. And it was launched in 2013, so that was already quite a while ago. And we think that it ends data acquisition maybe around 2025. If all goes well, then it's basically when the fuel will run out to maintain its orbit. Now, Gaia has a very specific design. It has two very big mirrors, which you see inside here in the payload module. And these two fields of view are separated by 6.5 degrees. And the satellite is rotating slowly every 6 hours around the spin axis. As you can see here, it's speed up, of course. And on the bottom, you see this hat, which is the solar shield, basically to prevent light from the sun to come in. Now, and by this rotation, the two fields of view both scan a different part of the sky. And due to the rotation, and actually precession also of the rotation axis, will slowly, bit by bit, scan all of the sky. And it's not just observing the sky once or twice, it observes this a lot of times. So you see the average number of observations over a full 10-year mission is about 140 times. So we have 140 epochs during these 10 years in which we observe positions of stars, their brightness, and possibly also their spectra. For the spectra, there are slightly less epochs, but still, and this is also for the brighter stars, but still, this is a huge survey all over the sky. Now, what makes Gaia then so special? So, as I mentioned, unprecedented astrometric precision. So if one imagines looking at the moon at the night sky, You see the moon, okay, it's quite big. Some people landed there, some landed many years ago. If you imagine that there was a coin lying on the moon, the final precision by which we can measure the astrometry of stars, the brightest stars, is roughly the diameter of that coin on the moon as seen from the Earth, which is beyond anything that has been known before. The other thing is the three instruments. What I mentioned, we have a white light band for the photometry. We have blue and red photometry, which we also call spectral photometry. And then we have spectroscopy itself as well. And they're observed sort of simultaneously. What you see in a lot of other observatories is that often you have one band at one epoch, another band another time. We get them always roughly at the same time, which also helps us to analyze data in a more consistent way. As we said, it's a multi-epoch mission over the entire sky for 10 years. And it has a super high dynamic range, so it can observe things down to magnitude 21, but also basically all the stars you can see with the naked eye. So this is a huge span. Now also in data analysis, this is quite special. I mean, this is truly big data that we're analyzing here. Only the 34 months of data that we have been processing so far already amounts to 1 trillion CCD observations. And the way the processing works in the consortium is that we have a cyclic processing. So every few years we have a new data release, which I will come to. And we every time improve the calibration of all the steps of the data. And we reprocess all the data up to a certain point, which makes it progressively much and much better, not in terms of just volume of data, but also in precision and accuracy. Then this is a photo that Laurent made at the EAS conference this year, which very nicely shows the success of Gaia measured in articles or publications. So on the x-axis you see the year, and on the y-axis you see the publications per year. And what clearly stands out is here that when Gaia started producing or publishing more and more of its data, suddenly it took off as becoming one of the most written about mission in academia for astronomy at least. So here's an overview of these numbers. Again, that Laurent has probably been cautiously harvesting. So we see that there are tens of thousands of articles just about Gaia. And you see here that there are, you see DR1, DR2, DR3, etc. So these are the data releases that we produce with Gaia, in which we put out a certain calibration, a certain amount of data to the public. And every time they grow in extent and in content. And now we are at the focus product release. So this is a release of data between the official DR3 and the upcoming DR4, which will be 2 years or so from now. What is in this focus release today is these 5 different points. So there's something about omega Sen, very dense crowded region, which needs some special processing. Something about quasars, used for gravitational lensing. The talk of Nami, the star of today, will be about the LPV part. And then there are also 2 other articles, one about diffuse interstellar bands and also solar system objects. So you see there's a wide range. These are just a selection of the kind of science that can be done with Gaia data, which now appear in this data release. And now I'll give the word to Chris to finalize related to the kind of support to make this all happen from the data processing center in the Gaia activity.
Thank you. Already there. We have 70 users which we have to basically support. We have to give them the data. We have to prepare the systems for them. This is big support from Gregory Jevarda, who's here with us, and new guys that I'm going to introduce. So Daniel Kreff and Klaus Schoda, who are working on the new project I'm going to mention. But point is that we have quite a number of challenges. We have many users, we have a lot of data, we have tight schedules. Normally we have only several months to process all the data in order to be within the data release. It's a petabyte scale mission, so it's actually more because we have many generations of the data, so this accumulates to more than petabyte of the data. We have something very special here in Geneva. We have massively parallel relational object database that we trying to push out also for other scientific endeavors. And we also leading some external to Gaia, but linked to Gaia projects. For example, now we are in the European Processor Initiative. So this is trying to boost GPUs, so accelerators in high-level languages like Java that we use. And this is what Daniel and Claude are doing, they started to do. And we're trying to actually expand. We're not limiting ourselves only to small fields or big field that is Gaia, but we're trying to kind of make the difference in the whole field. So DPCG is a core of this, and we're very, very happy to be part of the FPR and all the data releases. Then we have another thing. This is another side project we have. It's called Gaia Vari. You can see the poster outside. You can see the postcards here. So fetch yourself if you please. We prepared for data for the citizen scientists. We prepared carefully selected data from data release 3 of Gaia, so they can classify. But this is not only so they classify in fun with this. It's also so they create an input for us to improve our classification for DR4. So this is quite successfully already on the second campaign. Around 1,000 people, 1,000 citizen scientists partook. We have already over 200,000 classifications, and we have a lot of things that we learned and that help us to improve for DR4. And now we also think that this input will help to basically it will be kind of basis for some publications that citizen scientists are co-authors of as well. And you're most welcome to join. So we're always happy to discuss there and meet them. And okay, this is my part. So now we're going to invite Nami, the star of this event, who's going to talk about long period variables in this focused product release.
So good afternoon, everybody. It's really my pleasure to be here and to present data coming out of this FPR. Data that we have been producing here. It's really incredible data, and I will try to convey you some of the feelings that we have. We saw the data, we analyzed them, and now we publish them data release after data release, and this specifically in this focused product release. These are long period variables. We are a core team in the Gaia consortium with myself, Thomas Lebzerter, Michele Trabucchi, and Isabelle Curtailli, who have been working on these stars in the Gaia consortium. And of course, as was mentioned before, that's embedded in the variability analysis that is led by the Geneva group and the full thing within the Gaia consortium. And it's really a fantastic collaboration that is being done. So I will introduce that first, the long period variables. What are these objects? They are very important objects, as I will show you, and it will give you the flavor of all the impact that this data can have. And then successively, I will show what each data release has brought to this field from Gaia. And actually, each data release has added the data product of one of the instruments of Gaia, main instruments of Gaia. So in, So in the first release of the FPV catalogs of Gaia in DR2, we were based on photometry and of course on astrometry, parallaxes, and so on. In DR3, we make use of the spectra that are given by the RP spectrophotometer. In the DR and in the FPR here, we use the other spectrometer on board of Gaia to analyze the radial velocities. So let's start with long period variables. What are they? They are variable, and they vary regularly, periodically with given period or given periods. They can be multi-periodic, and those periods are long. Long meaning a few tens of days to several years, actually. So these are really very long periods, and together with these periods that are long, they are also characterized by variability amplitudes that can be very large. It can be up to 10 or even more magnitudes. The first of these long period variables that had been discovered about 3 centuries ago is Myra. And you see here a light curve taken by the Amateur Astronomer Association of the United States. And you see that it goes from, it spans about 5 years here. And you see the variability of MIRA, which goes on a period of 11 months. So it's almost 1 year. And it changes by almost 8 magnitudes. Now, it goes from a magnitude of 2, that's one of the brightest stars in the sky, up to magnitude of 10, you don't see it anymore. The eye is limited to a magnitude of 6. So the faintest star that you can see in the sky is about around 6, depending on the people, of course. Which means that for a good fraction of the time you see it, and if you come back 6 months later, you don't see it anymore. That's really amazing what these stars are. What are these stars? So I plot here on this diagram on the background, I took all the stars that have large amplitudes in the DR3, in the DR2 data of Gaia. And on the upper right part, you see these stars which are here, those are the long-period variables. This diagram is the color on the x-axis, so you have blue on the left, red on the right, which is a proxy for the temperature at the surface of the star, so the hottest and on the left and the coolest on the right. And on the y-axis, you have basically the luminosity, the magnitude actually. And this is the absolute magnitude, which ranges about 10, 12 magnitude. You see that all the stars are concentrated on a region, which is called the main sequence, where the stars burn hydrogen in their core. The LPVs are not there. They are much redder and much more luminous than the main sequence stars, which are the most common stars in the universe. Now, plotted on these data points from DR2, I have added tracks, models of stars that are computed here at Geneva for different initial masses. So the sun, typically with a 1 solar mass star by definition, starts here at the beginning of its life, then spends most of its life on the main sequence here before going on. After exhaustion of hydrogen in the core, it gets redder and larger radius and luminosities, and eventually would end up in these long-period variables. So the sun will become a long-period variable at the end of this. And the same thing would be for smaller mass stars, as well as larger masses up to 5, and actually we can show that up to 7 or more, it goes through the LPV regions. Which means that these stars, the majority, probably 80% or more of the stars in the universe will pass by this stage. That's an important conclusion as well. Now, that's for the masses of these stars. What are the ages? Well, the ages, if we take the longest period of life of a star, which is during the main sequence when it burns hydrogen, you see on the x-axis you have the mass from 0.5 to 3.5, and it gives you typically an estimate of the age. So these stars would typically have actually a large range of ages from a few hundreds of million years to several gigayears. Okay, so what are their properties? There are a few properties that make them very interesting. One of them is that they are period, of course. Now, if we take on the period on the x-axis and we plot the luminosity of the star, this is the distribution that we get. This comes actually from the stars in the Large Magellanic Cloud, satellite galaxy to our galaxy with the Audard data, and we see that they are relations between the periods and the luminosity, which means that if you get the period, that's easy to measure, you just get the light curve, you have the period, then you can deduce what is its luminosity and hence its distance. The fact that there are several relations makes things a little more complex, but we are working now in our team as well to develop this scientific aspect. Among these, the fundamental mode pulsator is here, the sequence C, and that's typically where MIRA would be. Period luminosity relation is one thing. Actually, a work that has been done with Michele Trabucchi showed that from model predictions that a period on the x-axis, on the y-axis, and age on the x-axis should also hold, which would be able to predict ages as well for these stars. And finally, a last property of these stars that I want to mention is the chemical abundance. Most of the stars in the universe are oxygen-rich, meaning that in their envelope, at their surface, the number of atoms of oxygen is larger than the number of atoms of carbon. That's the case for our sun, it's the case for most of them. In these LPVs, we find some of them which have the opposite, more carbon than oxygen, and these are called actually carbon stars. It's not that the full star is carbon based, but in the envelope, it has more carbon atoms than oxygen atoms. And this is another interesting conclusion that we made from the DR2 data, combining the Gaia photometry with infrared photometry, typically from 2 mass here. We can distribute in a given plane of combination of colors and luminosity, and we can distinguish very well the ones which are oxygen-rich on the left and the ones which are carbon-rich on the right. And you see that indeed there are many. Why is this important? It's first to understand the evolution of these stars, but also because these carbon which are in the envelope will be eventually expelled in the interstellar medium. These stars will end up as planetary nebulae and then white dwarfs, and the majority of their mass will be released in the galaxy, and those are carbon-rich. And actually, part of the carbon which forms us comes from these stars. Okay, enough for this introduction. Let's go now for the different data releases. The first one on LPVs was data release 2 in 2018. This is the distribution of all the stars, LPVs that were published in the catalog. We had about 150,000 LPVs published, and for about 90,000 of them, we could derive a period. Remember, DR2 was only 22 months. Those are long periods, so you need a long baseline in order to get accurate periods. So that's a start. In the literature, there were about 500,000 known, roughly. So it's not bad. I mean, for a first release based only on 22 months. And this is all sky, which is unique. It's all sky. And in addition, it has both the global photometry in G and the colors in the blue and in the red. And with these, you can position them on the HR diagram. But because it has many epochs, not only you can position in the HR diagram as shown at the beginning, but you can also follow how they move in there. And actually, this is one of the results as well in DR2, where you see that, so this is a color and luminosity magnitude on the left. And these are all the points in the back. When you see that, you think it's static, but actually look at how they move in there. Their color change, their magnitude change. This is all due to their variability. And yeah, okay. So first catalog of LPVs was published for DR2. You can go in these ones. Let's go now to DR3. DR3 makes use of the spectra that are recorded from the RP spectrophotometer. So this is Gaia, and you see here, no, you don't see my pointer there. You see here the Gaia, you have the focal plane, which is here, and you have the photometers, which are prisms. You have the BP on the left, which goes on the right CCDs, and RP here, and you have the path of the light, which goes here, goes through this prism and produce a spectrum on the focal plane. And here you see a picture of, on the lower left, you see the picture of the real stuff as it's taken before Gaia is launched, of course. Now, this is two examples of spectra that come from this are big spectra. So the red one, which goes actually quite a little in the infrared. The pseudo wavelength, whatever, this is on the left, this is less red, and this is much more red on the wavelength, so shorter wavelength on the right. On the top, you see the spectrum of oxygen-rich ones, and typically you have TiO bands. Those are cold stars, so you don't have atomic lines, but you have some, but not here. But you may have broad molecular lines, which you see here. And the carbon-rich is, you mainly have carbon-based molecules, and this is CN, which is around 800 nanometers. And you see that the general pattern that the spectrum shows is quite different between oxygen-rich and carbon-rich. And that's the main thing that we use in order to identify and classify between oxygen and carbon-rich. Typically, for example, you see here you have 1, 2, 3, 4 peaks. Here you have only 1, 2, possibly 3. So these are the type of things. Actually, what we do is we base on the distance in the pseudo wavelength between the two highest peaks, and this allows us to classify between carbon-rich and oxygen-rich. And that's unique. We can do that for all the LPVs that are published in DR3. This is how it actually goes with time. You see here is the same spectrum that was shown just before. You see on the lower right the different spectra that are taken at different times as Gaia scanning goes and passes through this star. You see on the upper right, that's the variability of the luminosity, the magnitude in the G magnitude. The second, just below, is the color. And if you combine the magnitude and color variation, you get the loop that you see in the left HR diagram. And you see that it's really not a single point. It really goes very far. On the lower right, you see the spectra that varies. Because of this large exclusion in the color, the surface temperature also changes a lot. If the surface temperature changes a lot, the spectrum itself changes a lot. So you cannot just take all the spectra, make a mean, and analyze it. It wouldn't fit to a real star. You have to take every individual epoch spectra, and then you can analyze them. And you see, for example, here, when it's the faintest would be the coolest, then you have many more molecular lines than here, where you see that the molecular lines almost disappear because the star gets hotter, and when it gets hotter, you have molecules dissociate and you have less of them. Okay, just to summarize, in the DR3, what we had, we published about almost 2 million. We are going from 150,000 in DR2 to almost 2 million in DR3. That's a huge jump. And the carbon stars, about less than 1/3 are identified as carbon star candidates. Those should be, of course, confirmed by further studies. And then you have subsamples here of good parallaxes, or the ones which are in the Large Magellan Cloud. You see the numbers which are there. If you want to play with them more, this is the paper that describes these data. Let's come now to the FPR. The FPR, that is the object of today's release. The FPR now makes use of other instruments that is on board Gaia, which is the radial velocity spectrometer. This is coming back again to this picture of Gaia. You see here on the RVS detector, but you see here the grating that allows the light that passes through to have high resolution dispersion and high resolution spectra. And this is the image of this grating in real. Okay, now just a little animation to understand what's going on, not only in the spectrum, but more specifically for the LPVs. So you have an animation of typically a minor star. You see it contracts, it expands. I mean, the radius variation can be huge. Huh? It can be several times. And the radius of these stars can go up to several hundred times the radius of the sun. Okay, now, probably most of you know how radio velocities are measured. If you take the spectrum, this is just an illustrative example. If you take the spectrum, in the envelope of the star, you have some elements. These elements absorb light emitted by the star at given wavelength, which makes them darker, because they are less, they are absorbed by the star. And this makes these lines in the spectrum at definite wavelength. Now, when the star expands and contracts, the layers come to you and go back from you, and this produces a shift of these lines, as you would expect. That's how you see it. Of course, the amplitude here has been much exaggerated. Okay, now, this is not what Gaia observes. This is only an illustration of how the principle of radial velocity detection. What Gaia observes actually is this RVS is a very small window around the calcium triplet. I put it here on the very red, actually it is between the infrareds, but whatever. It's a very small region, and there Gaia gets the spectrum and analyzes the radial velocity shift. Second thing to note, these are not lines, right? Because these are non-period variables, so they are code. And this is typically the spectrum that you see. You see a few lines, right? On the right, you see 3 lines. In the middle left, you see 1 line. But globally, those are molecular absorptions. So molecular absorptions absorb a little everywhere. So you don't see actually the continuum of the emission of the black hole emission of the star. So this is what Gaia detects in these red giants. And when you make it move, going backwards, expanding and contracting, this is what you see. Well, not exactly neither. Again, this is an illustration. What is different with reality? Well, in reality is that when it contracts, it's hotter. When it expands, it's cooler. And hotter and cooler give different spectra, which is not shown here. So that's another difference. We just took here the Alex Lobel, who made this present animation, just took one spectrum, and actually it should also change its shape. Okay, now we have these radial velocities that's performed by another team in the Gaia consortium. They're really great. Actually, the way they do it is that they have template spectra of red giants of given temperatures and metallicities and chemical composition and so on. And then they try to fit to the observed spectrum and see how much the observed spectrum is displaced with respect to the template spectrum. And what is remarkable is that for DR3, they didn't really have carbon star templates. So that would have been an issue, but actually it works quite well. And one way to see it is to plot the mean radial velocity. That was already published in DR3. That's the mean radial velocity, not the epoch variable. And if you plot the mean radial velocity, even including carbon stars, you can see actually the imprint of the rotation of the galaxy. You see here, this is positive radial velocity in red, and when you go to the blue, it's negative radial velocity. So negative radial velocity will come to you, and the red one, it goes away from you. And you see that on the right side of the galaxy, this is a galactic projection, it goes away, and on the left side, it comes towards you. Okay, now what we do, whatever the mean radial velocity, is take advantage of the epoch radial velocity. And that's new in the FPR, and it's the object of this FPR. That's an example, a raw time series of one of the non-period variables published in this FPR. In the upper curve, you see, according to time, the value of the radial velocity of this star, whatever that is. And below you have the time series of the three photometric bands. So the red one, RP, in green it's the G, global photometry, and in blue it's the BP. Now you immediately see that this is LPV because the mean red magnitude is much brighter than the mean blue magnitude. Okay, now in this case, our pipeline, which analyzes the time series, gets out with a period of 256 days in the radial velocity time series and 261 days in the photometric time series in the G. Those are compatible given the period and the duration of the observation. This is all fine. Now, when you fold this time series with the given period, then you see better the full picture, and this is what is shown on the right panels. For that with 256 days, which is the radial velocity of the, which is the period of the radial velocity. Okay, now we have the radial velocity amplitudes, that's very important, and the periods. So these are the two quantities that we can get from all four time series. What can we do? So the first thing is to compare the amplitudes in the photometry in G and the amplitude in R. Now, you can imagine that if the star is expanding very largely and it has an amplitude of variability in photometry luminosity very large, you also expect that the amplitude of variability in the radial velocity be large, because this star goes much further away and comes much down. And you see globally, indeed, there is a relation between the amplitude in radial velocity, plotted in the x-axis, with the amplitude in G, in photometry, which is on the y-axis, and this is all fine. But this is not the case for the stars which are here. So what are these? Actually, these ones have radial velocities which are much larger than expected from their photometric amplitudes. And these are typically binary stars. So you have the red giant, ULPV, which it turns together with a more compact, typically a main sequence star, that is not visible nowhere, not in the spectrum, nothing like that, because the red giant is much more brighter than the main sequence. So the main sequence is lost, the signal is lost everywhere. So you don't see it. But however, because of the gravitational attraction of the outer layers of the red giant by this companion, the surface of the red giant is deformed. It's no more a circle, but it's like a pear. And as it turns around its orbit, whichever turns around the other, that depends on the mass ratio, doesn't matter. That's only an animation, an illustration here. But whatever the pair that turns around will show different parts of its surface and lead to variability in the luminosity. But because it also turns, it will also have a different variation in the radial velocity. And this variation in radial velocity is much larger than what would be expected just from its expansion and contraction. Now, this plot was done for on the black, on the upper left. We have highlighted all the sources which have a period in radial velocity similar to the period of photometry. But now, if you take my image of the pair turning around another unseen star, then if you think on the lower right, I showed two different configurations, they are symmetric, right? Totally symmetric. And going from one to the other, and then back from the other to the one, in photometry, you don't see the difference. But in radial velocity, you will do a full period. So actually the period in photometry, you expect it to be twice smaller than the period in radial velocity. And on the lower figure on the left are highlighted the points which indeed have a period in radial velocity, which is about twice the period in photometry. And indeed, you see that most of the stars that were in the ellipsoidal region that it's supposed to be, do indeed have this property. It's not always the case, so we cannot use that argument, and we did not use that argument to classify between the two. The argument that we used in this study is only based on the amplitudes. Okay, an example of such a case of an ellipsoidal. On the upper figure, you see the period of 194 days for the radial velocity, and for the photometry, you see about half of it, 96 days. That's very fine. And when you plot in phase, you actually see that the minima in photometry are not the same at half the period. Okay, now we are happy. We can exclude the ellipsoidals. We can identify them. They will be used for other studies. And let's come back to the sample, which is cleaned by these ellipsoidals. And let's plot another figure. And this is the period in the photometry on the x-axis. And on the y-axis, you have the amplitude of that same photometry. And what you expect is about the same. The larger the period you have, probably the amplitude will be larger as well. And this is indeed globally what you see on the left part of the diagram. All is fine. There's a correlation between the amplitude of the photometric variability and its period. But, again, you have a whole bunch here of stars which have very long period, even longer than the ones we just analyzed. But small amplitudes relatively, and there is no specific correlation. These have been a mystery, and I would say still are now, of what nature they can have. This is what we call long secondary periods. Why long? Because they are much longer than what you would expect from a simple pulsation. So it's not, its origin cannot be from pulsation. And it's secondary because usually it comes together with the signal in the light curve of other periods that are compatible with this one. So it's a signal which is added to the normal expected signal of a pulsating red giant. This is an example of such a thing. So you have here the very long period of 800 days in the radial velocity, and a very long period as well in photometry. So they are also compatible with one another. And where the difference here of 50 days is not significant given the duration of the observation. And what these are, it is suspected that this comes from the presence of a cloud of dust that orbits around the red giant, to which can be associated a small mass companion, maybe even a planet type of companion. And this is what has been illustrated here in this infographics that has been done by Isa, where you see the three cases of a pulsation, the standard, I would say, case, the binarity, where you have this deformation of the star that leads to the observations, and the occultation by the dust. Okay, now we come to the end. Before that, I show two applications of these FPRs. First one is in the color magnitude diagram. So remember the color on the x-axis and the magnitude on the y-axis. This is a zoom on the cold, bright side of this color magnitude diagram, where all the LPVs are that I showed at the beginning. Now we can distinguish between these two groups. The pulsating and the long secondary periods, they form a good extension on where they should be. And we see that the ellipsoidals are more towards the red giant branch, actually, which is a very interesting case. Now, even maybe more interesting is the period luminosity diagram. This is a Wassenaar index that is a proxy for the luminosity, it doesn't matter. And we see that, you remember these period luminosity relations, because Gaia can measure the parallax and distances. This is the first time that we can do this diagram, actually. And you see that the pulsating stars are on the different relations that we expected, the fundamental which is here, and then the first harmonic. The long-secondary periods have their own period luminous simulation that was known already, and then the ellipsoidals are also distinct in these cases. So in the FPR, we publish actually a small subset, well selected, to give a teaser to the community of about 10,000 sources. You say, come on, 10,000 sources. In DR3, you publish 2 million LPVs. Why 10,000 sources? Well, there are several reasons. One is that the RVS, the spectrometer on board of Gaia, can only analyze the brightest. But even that, we would have more than 100,000. Then we did some more selection and so on. I just want to say that 10,000 is 10,000, knowing that in the literature so far, we just have a dozen or maximum a few dozen of LPVs which have radial velocity time series. So compared to what is known in the literature, that's a factor of almost 100 more sources, good enough for the community to analyze. Okay, so you can have more information on the paper that is being released today. And for DR4, just to say that all the data will be published. You will have all that has not been published now. And together with the epoch spectra and so on, you will have more than 60 months of data. So we can only play with all that. And I finished with a nice animation that Krzysztof here has done to show an animation showing a sample of these FPR LPVs distributed on the sky, where you see how they expand and contract. The color is related directly to the mean BPRP color of the stars. And the time of expansion and contraction is proportional to the period, to the real period detected. Now, 10 seconds is 1 year here. So it gives you an idea of how long the period can be. And Krzysztof has added very nicely the orbit of the Earth around the Sun, just to see how this relates to the period of variability of these non-trivial variables. Thank you.
Thank you very much, Nami, for this vivid explanation. Any questions? This is time for questions.
Yes. Well, I can speak loud. You will take the microphone. Hi, Nami. Thanks. Great talk. Just a technical question. I'm not sure to understood. The data reduction is done on the satellite, so you get the RV, or so the spectrum are available.
No, the spectra are downloaded, and everything else is done on ground.
So do we have access to the spectrum?
Not this one, but for DR4 you would. Now, there are some mean spectra that have been published in DR3, yes. But for a sample, still a large sample of stars, and these are mean spectra, so you won't be able to do epoch photometry or epoch spectrum analysis. Photometry, yes, with what we published.
Nami, can you say a few words about the evolutionary stage of these stars? You did not talk about the evolutionary stage.
Okay, the evolutionary stage of these stars, so they have exhausted their hydrogen. Then they went through the phase of called helium burning. So they have also exhausted their helium in their core. So they are now with a structure which has the core, which is actually so compact that it is degenerating the electrons, and that will be the remnant in white dwarf. So you have kind of white dwarf on which you have one hydrogen, helium burning layers, then another hydrogen burning layers, and then the huge envelope. That's the stage. The next stage of this is that the huge envelope, you know, the core, what will become the white dwarf, is about 0.6 to 0.8 solar masses. So anything that exceeds that, if you start with a 3 solar mass star, is in the envelope. That envelope will be pushed away by radiation to the interstellar medium will form planetary nebula, and what remains will be the white dwarf, which ends in the white dwarf graveyard.
Thanks. So they should be at some stage moving from red to blue, right?
Correct.
Can we see that in the Gaia?
So they should be able to move they will move from red to blue, but they will no longer be long period variables because they won't have their envelope, and we could be able to detect them in Gaia. It's actually one more package that we are working on to try to detect these real-time variations of these stars. Yes.
Thank you.
We actually have, I think, one animation done together with U8 for DR3 that we show the model how it's going.
Now, in the literature, we already know such stars. Sakurai objects, for example, is one of those stars which is crossing the HR diagram currently now. And there are maybe 2 or 3 others that we know in the literature. We expect Gaia to be able to find many more. It occurs on a very short time scale, so statistically, you don't expect to observe many of them going from the red giant to the planetary nebula.
But at humans time scale, it takes time, no? How much?
No. Well, the more massive ones can move on a human time scale.
What, years or months?
No, years, tens of years.
Tens of years, okay.
Thank you. We can conclude this presentation of Nami, and then we can invite Marc Audard.
Hope you can hear me. So I'm the one before the apero. I hope I can explain why I will be talking to you about DR3 and later DR4. I mean, you had a very good presentation by Barry about what Gaia is capable of doing, by Nami also specific results that we've done, but we've been doing a lot of things here in Geneva, but also within the Gaia team in general. And that it is more of a recap for the audience here, online and physically, about the different capabilities and output of Gaia. And here we focus specifically on DR3. Let me just put this one a bit better, otherwise it will fall. Here, good. This is Gaia, and you may have seen this kind of plot here where you have about 1.8 billion stars which were detected. Out of these, you can get a lot of information that you find in the archive. Photometry, obviously. Where is it? The photometry aspect. The astrometry, you should see it here. At the bottom on the right. Astrometry, position, distances. You see for about 1.5 billion. Radial velocity, as Nami mentioned, about 33 million, but the mean spectra currently in the archive. There's some information about classification. People are interested in knowing if it is a young star, not a young star, and so on. What are some of the properties, effective temperature, etc. We have also mean spectroscopy being delivered for a number of sources already, where either through low resolution spectroscopy and high resolution spectroscopy. But one thing which is interesting is at the center of the coordination unit on variability is basically that many of the stars in our galaxy are actually variables. And indeed, we have seen that we have detected many of them through classification, maybe through photometry. And in DR3, we have published about 10 million sources. And this was a giant leap, basically, to go from about a few 100,000 in many catalogs, as you can see on the left, ground-based, Catalina, Pan-Stars, 2017, Atlas, even 1.5 for SuperWASP. But look on the right-hand side, this is the Gaia output. In DR1, I was not yet there, but 3,000, not a huge number, but very precise already. And this was really a showcase of the capability of the variability analysis. DR2, 550K. This is already a huge number. I mean, of course, compared to the 1.5, still a bit lower, but a huge number already with many, many types of stars. DR3, 10.5 million. And this is a logarithmic scale, and we want to achieve with DR4 already about a factor of 10 again, with more variable stars, because we know we detect them, but we are not yet releasing them in DR2, DR3, simply because of the way, as Barry mentioned, we are iterative. So now, many of the people here have studied astrophysics or have been at least in this department long enough to know about the Hertzsprung-Russell diagram. basically kind of a measure of the effective temperature, or here color in the x-axis, luminosity or absolute magnitude in the y-axis. And in principle, when you know all of this information, you should know exactly where your source is, what kind of star it is, what kind of luminosity it has, if you can correct also distinction. But variable stars show, and the NPV was a very good example, that things are moving on timescales of a human, and even shorter, even sometimes seconds or days. And look at this HR diagram. It is moving all over the place. This is an animation done here. I think we'll redo it again. So I think it's a very nice one, so that you can have a look. Restart. It doesn't want as usual. Let's go this way. Now, pick your favorite star. Most of them are variable. Of course, my favorites are somewhere there, the Y source above the main sequence. We've seen a lot, very madly, as you can see from the LPVs, from Nami, but you can have cataphysic variables. We have white dwarfs, we have Cepheids, we have Arlaris, many kinds of objects there. And what is just showed to you is, let's just be cautious. When you have an effective temperature for a source which is variable, well, what does it mean in some cases? It can change as a function of time, and especially if you're focusing on colors and magnitudes. From the perspective of the variability tree, I mean, this was a very nice plot done by Nami, but also by Laurent. Altogether, they had this kind of tree where you can see the difference between what we call extrinsic and intrinsic, between stars which are eclipsing, microlensing, and some stars are eruptive pulsation aspect. And in yellow here, you can see basically the output in the R3 of what we have produced, either through what we call classification, but also SOS. We've covered most of the variable stars already in the R3. We have still a few more. There is this microphone hole. Let's go back. 1 second, please. There we go. On the top right, you have also AGS, not a star, an active galactic nuclei, black hole, but it is also varying very significantly, and we have detected them and classified them. So if you're looking into our so-called summary paper for the R3, you can see that many things, this is on the left, the pie chart, are eruptive and cataclysmic in a small fraction, pulsating about 30–40%, but we have many which are eclipsing. Binaries are huge numbers, rotation modulation, like basically the sun, so like magnetic activity, but we have also these 10% of AGS ones. And what was very interesting was a work done by Barry, which was basically taking into account the fact that Gaia is so good of a spatial resolution that it can detect slightly extended sources. And you remember about the animation about Gaia spinning and spinning. And this is basically in the way it is looking for sources which are slightly extended. It can detect some kind of or mimic some kind of variability, a pseudo variability, simply providing here, as you can see on the bottom right, as a magnitude changing as a function of this an angle, basically along where the scan is and where the source is also resolved. And this is interesting because we were able to use it to detect 2.5 million galaxies. It's not that the galaxies are variable, they're pseudo variable, but this allowed us to have a large fraction of galaxies detected through this thing. It is important, and we'll also try to emphasize it in the R4. So if people are looking into variability, they should take into account this effect there, because it creates basically spurious signals. And this is something we're trying to do. In terms of the variability pipeline, and here, this is processed at DPCG, coming from software either done in Geneva or from our colleagues throughout CU7. But you can see that we're using at the top left in the R3 34 months of photometry, G, BP, RP, so-called field of view, but we had a little bit of information from the RP spectrum. That's what also Nami showed, for example, with the wavelength differences. In some cases, radial velocity time series. This was done with Cepheid and Arlaris in the R3, in the FPR with the LPVs. And then we can get also, we just try to clean out things with the operator. We can make calculations of many types of statistical parameters. And then we try to characterize basically or detect basically variability, either through what we call the general variability detection, as you can see on the left, which essentially at some point is using supervised classification, using a large fraction of classes, among them also these famous galaxies as a sort of variable. But we have another tree, which is so-called special variability detection, which is basically for things which are not always easy to detect from the general variability detection aspect, like short time scales. This is more focused by Laurent, micro-lensing events, or planetary transit where there is a mix between things. But you can see already here that we have a wide variety of variable objects. And if we're looking into the classification aspect only classification, I mentioned the 2.5 galaxies, and you can have a wide range of sources. I'm not going to go in all the details. My favorite are the Y source. We had about 80K new with my colleague Gabor Marton. It was already about 40K new ones compared to what we know in the neighborhood, but there were many more from LPVs, as was described by Nami, micro-lensing, and so on and so on. We have a large number of sources, and if you're interested, look into the very classifier result. The spin-off was also Gaia, was already presented by Chris, but it will be used also as an input for DR4 and later DR5, coming from the citizen science as well. From the SOS perspective, okay, flags, very nice slide from Nami here, where you can see the involvement of Switzerland. Of course, we're CU7 and DPCG, but nevertheless, many of our colleagues are involved and are leading the work packages on our libraries, CEPID and so on. And there have been several results out of it. There are sometimes overlapping. In many cases, these were coming from the classification aspect. If you're not very keen in terms of understanding the data that we have in the Gaia archive, just be aware, at least, there is a classification output and there is an SOS output for people who really dig into the aspect. Look, for example, if you're interested in the RLI and Cepheid, they have detected it. We have detected it with classification. Then our colleagues have taken them as an input to look into more details, confirm them, not. And then if they were confirmed, they divided our RLI Cepheids. Then what are some properties? What is the period? What is some extinction? And so on and so on. And these are so-called specific object studies, SOS. It's not that we're trying to get help from people. And there is a good overlap, but not always. And as you can see, there is a certain fraction which goes into it. So if you're interested in more large scale sky, look into classification, for example. If you want to focus on specific objects, look into the SOS and think in between as well. Two small results, just as I mentioned here, exoplanets is a big thing in Geneva, of course. But also Gaia has done some work also on it in DR3s, 173 candidates, 41 were new, 2 were conferred by radial velocities as well. And you can see on the top, for example, light curves, as you can see from G, BP, and RP with some colors, BP blue, RP for red, the one with the G is in black. And in the second one from the top, you can see already the folded light curve, and you can see there's a dip every time at the phase 0 in the 3 bands. And then with the model, you can see that it mimics relatively well. And this was a good example where it worked out. I just mentioned for some people who might be interested, look at the biplanetary transit table and not the one from the 13th of June. There was a small mishap, but it has been relatively swiftly corrected in the archive. Candidate compact companion, also a very exciting thing because of gravitational waves aspect of black holes. From the variability in the light curve, we can see ellipsoidal variation, and out of it, our colleagues from Israel have basically detected these short period candidate ellipsoidals, and out of that, they can make a model and assume a certain modified minimum, or get a modified minimum mass ratio, and if it is above, it has a certain high chance that the secondary companion is compact, so bearing a neutron star or black holes. Of course, this is photometry only. We need confirmation through radial velocities. So Gaia, DR3, that's what I tried to show in a few examples. This was a very nice plot made by Barry, where you can see indeed this iterative approach that Barry mentioned, 40 months, 22 months, 34 for DR3 and DR3. FPR is right now, it's using data from, or sources from DR3, specific for the LPV, but adding the range of velocity. DR4 of the order of 2025, 66 months, so we already double time scale as there, and eventually also with DR5 a little bit later in the future, this will be all Gaia data until the end of the fuel, and you can see it's foreseen of the order of 2024, 2025 there, so we'll have about, again, another factor of 1.8 something in duration there. We can be more precise in astrometry, but also look into things in more details and better calibration. So toward Gaia in the DR4, not before the end of 2025. This is the official statement as announced about this exactly. This is one of the major points from the community perspective. Apart from the interest of the output of Gaia DPAC, some people will try to use also data themselves. And one of the interests is all Gaia epoch data, so basically these transit observations will be published in photometry and spectroscopy from the BP and RP, but also from the RVS. So this will be out to the community to do better than Gaia DPAC. I'm sure there will be very clever things to do. There will be other projects. Here, example, the only available variable star and solutions. So as I say, we go further, but also non-single stars. So when there are binaries, there could be also a list of exoplanets as well. Basically, as I've shown, the length of time will be the time series will be doubled, so it will be a better light curve characterization, very important for the aspect of LPV, but many other objects also will profit to a certain degree of the better calibration that we should have as well. New variability types, we've covered a lot of things, but we can think that we can get a little bit better for a few objects which are more difficult at this stage. Also trying to get some kind of calibration or score probability. We can get also from our colleagues doing the SOS aspect, new characterization, more details. I mean, in the last few days, I've uploaded many parameters already where people have said, oh, I want to do this, I want to publish this, I want to publish this. So they will have tables basically, which will be large. Already, the so-called variability pipeline is producing a huge number of tables in the Gaia archive on top of the simple for whatever it means, Gaia source. So we are already producing a huge number of products ourselves in the R3, and it will be even more in the R4. And one of the interests that we want to do is try to use more complex data. Photometry is very interesting, produces a lot of very high, nice data and quality, but we know that we should try to use all the capability of Gaia. This is one of the interests of Gaia. We can do also spectroscopy at the same time. We can do astrometry for those specific objects. And for example, we want to make use, for example, like Nami has done for the XP, for the RP, we can use the subbands, for example, if you want to measure H-alpha variability, this is one interest. If you want to look into microlensing, let's see if we can have information for astrometry time series. So I cannot show you more because, well, this is not public, but at least we're trying to get better and better even in the R4. And this is already what we're trying to say in this slide. We've gone to 10 million variables. This is already a huge catalog for the community. And we're going to go to 100. This is the largest Soul Sky catalog of variables. It will be even better with scores and everything. Classification, SOS, galaxies, even if you're interested in things which are not variable but are detected like that. So with the R4, this would be already big jump from the R3, which was already a huge giant thing from the past. Thank you very much.